Again, I'm going to do a quick test for my friends out in the back. Can you raise your hand if you can hear me just fine? Great, thank you. All right, so welcome to another lecture on constraint satisfaction problems. First, a few announcements. So first of all, homework 1 on search was due yesterday. I hope you all got to submit that. You can now go on Piazza and click Show Answer to figure out the explanations for things maybe that you weren't quite sure about. Then we have Project 1 that we talked about last time. Again, it's due on Friday at 5 p.m. Start early, ask questions, it's longer than most. Optionally, there's a Project 1 mini contest, and the mini contest is due Sunday at midnight. I encourage you to participate in the mini contest. I know it's optional, it's sort of extra work, but it's probably one of the most fun part of this class where you get to compete against each other and against our GSI's agents. And those of you who stand out, then we might actually talk to you later on in the semester about doing some AI research. So I certainly encourage you to take these optional contests seriously. And then finally, homework 2 on CSPs is about to be released, if it hasn't been released already, and it's going to be due on Monday. Good. Now, another piece of announcement. We compiled an approximate count of how populated the discussions are. Okay, so here you see it here. We have it for January 25th as well as yesterday, February 1st. And if you are one of the people who is maybe going to, let's say, this one. Whoops. Sorry. New technology here. So if you're going to this one, you might consider switching to something like this one over here or that one. Of course, it's totally up to you, but we wanted to show you these numbers. And I'll leave you a couple seconds to look at them. Just to kind of make sure that you're getting kind of the biggest bang for the buck out of these discussion sessions. All right. Any questions about logistics? Good. So let's move on to constraint satisfaction problems. We started talking about constraint satisfaction problems last time, and we kind of started getting to the fun part, which is how to actually solve them and how to solve them efficiently. And that's what we're going to be building on today. We're going to do a little recap, just because some things were a little bit rushed towards the end of last lecture, so we're going to recap filtering, and then we're going to move on to a few other techniques, as well as my favorite. Okay, my favorite is local search. So local search is something that's not specific to constraint satisfaction problems. It's a really important technique. It's really, really simple, and it can be immensely powerful across many, many different problems in the real world. So whenever I get a problem that looks anything like a constraint satisfaction problem or an optimization problem, I think of local search or local search-like techniques as the first thing to throw at it. Okay, so hopefully we'll get to local search. Let's remember constraint satisfaction problems. So what were constraint satisfaction problems made of? What were the ingredients? Yes?
Variables, domains, and
yes, we had variables. In the map coloring example, these were the various regions of the map. Then we had domains for each of these variables. They could start off with all sharing the domain, like red, green, blue, but they could also have specialized domains. And then we were looking for an assignment of values from the domains to these variables. Except we couldn't assign them in any kind of configuration. We had some constraints. Constraints like assign colors to these variables, but make sure that when you have two adjacent regions, they don't share the same color. You don't assign them the same color. So those were constraints, and we thought of this problem as a search problem. We can apply search techniques to solve these kinds of constraint satisfaction problems. And kind of a main idea was to do something called backtracking search. Backtracking search was basically depth first search in this space, except where we started with an empty assignment like that one. So we have the map, but we haven't assigned any colors yet. Okay, and then we keep on making an assignment, making another assignment, making another assignment, and so on. The successor function just makes us take one variable that's not assigned yet and assign something to that. Who can tell me what backtracking search adds on top of depth first search? There were two ideas that backtracking search added on top of just running depth first search on this problem. Who remembers that? Yes?
If you find a node which comes with the previous assignment, then you don't need to check that node at all, so you backtrack immediately instead of going all the way.
That was one idea. And then there was a second idea, or a first idea, depending on how you think we presented them. What was the other one? Yes?
Checking to see if it's a goal state before you click on the priority.
That was, so we were careful about checking constraints as you go. That was the answer from there, yeah. But there was something else. We checked constraints as we went along, but we also actually fixed the ordering of the variables. Because we said, at the end of the day, orders are commutative, right? This is unlike maybe other kinds of search problems where if you take action 1 and then action 2, you end up in a different place than if you take action 2 and then action 1, right? But now with constraint satisfaction problems, we don't have that property. We can assign one variable and then another, and regardless of what order we chose, at the end of the day, we're going to have those two variables assigned, okay? So we can actually pick an ordering ahead of time. We haven't discussed what that ordering should be, but we're going to pick an ordering ahead of time. So for instance, we're going to go from that state, and we're going to say our first variable that we consider is going to be that leftmost one. It's called Western Australia. And the successors are Western Australia equals red, Western Australia equals green, Western Australia equals blue, right? So that was the first idea. We'd start with one variable instead of, the alternative would be to also consider Northern Territory, to also consider all the other things and all the values that they could have. But we're not going to do that. We're going to pick one variable at a time in our ordering. And so that was the first idea. The second idea, as mentioned over there, was to check constraints as we went along. So that means that if we pop up that successor there, which is this one, Western Australia equals red, then its successors are going to be Northern Territory. Let's say Northern Territory is our next variable. Northern Territory equals green, Northern Territory equals blue. We're not going to look at Northern Territory equals red because we decided we'll have this kind of incremental goal test, a fail check, which basically says, okay, it's true that if we had, let's try. It's true that if we had this kind of map here too, where both of these guys would be red, that node, technically it's not a goal, but it has successors, so we can move on, right? But we're not going to consider it because we already know that no matter what assignments we're going to do going forward, we're still going to be in trouble because we're already violating a constraint, okay? So that was the idea with backtracking search, and then you have this incremental goal test. You can think of it as this constraint satisfaction RoboCop saying, no, I can see that this is not going to go somewhere good. There's no light at the end of this road, so we're not going to allow you to go there. And then we move on and move on. So that is backtracking search. We can see a quick demo of this. So here's a graph. And what we're going to do is going to do backtracking search with no ordering, nothing fancy. And what's going to happen is we fix an order of the variables. And in this case, we fix the ordering to go kind of this way. These ones first, and then these ones, and so on. So we take the first one, we assign it blue. Normally in depth first search, we would take the next one and also assign it blue. But now because of our idea of, okay, check constraints as a go, this is going to be red. Then we move on. That can be blue. This can be red, blue, red, blue. Now, for this next one, the only thing we can do is green, right? That's the only thing that we can possibly do that actually meets the constraints because we already have red here and we already have blue here. So the only thing that this can be is green. Okay, and then we move on and move on and move on, and eventually we realize that we're kind of in trouble because now we have to assign something to this one. But check this out. This one's connected to this one, and this one's blue, so it can't be blue. It's connected to this one too. This one's red, so it can't be red. And it's also connected to this one. Okay? And it's green, so it can't be green. So now we have to backtrack. Remember this example because we'll come back to it later. So we backtrack, let me play this, and we go, and we go, and we go. And it takes a long time. And I'm not going to let this finish. But that's backtracking search. And obviously we can still do better, right? So we started talking about one way to do better, which is filtering. The idea with filtering was that we're going to actually start detecting these inevitable failures even earlier. With backtracking search, with this idea of checking constraints as we go, we were already doing a better job than depth first search. We weren't assigning blue when we just assigned blue to the neighbor. That was one way of detecting failures earlier than depth first search would have. But we can detect failures even earlier by being even a little bit smarter about what's going to happen. And then we're also going to talk about ordering and structure as different ideas for improving backtracking. So filtering. All that filtering does is it's going to keep track of domains of the unassigned variables, and we're going to cross off from their domains things that we know are not going to work out. And the simplest idea of filtering is something called forward checking. We talked about this last time. Forward checking basically says whenever I make an assignment, I'm going to look at the neighbors, I'm going to look at the variables that are not yet assigned, that have constraints with this variable, and I'm going to cross off from their domains inconsistent values. So for instance, let's say I go and I assign Western Australia red. Western Australia becomes red, and what did I do? Well, I know it has a constraint with Northern Territory, and Northern Territory can't be red anymore. So I eliminate red from the domain of Northern Territory. I do the same for Southern Australia. Then I move along. Let's say my next variable for some reason is this guy here, Queensland, and I assign it green. If I assign Queensland green, then now I know that Northern Territory also can't be green. I remove that. I know that NSW can be green, so I remove that. And I know that in Southern Australia, that can't be green, so I remove it as well. That's the idea of forward checking. And you keep going. So let's see forward checking also in this demo. So now we're going to do the same thing, except we're going to say, okay, now with forward checking. Immediately what you see happens is that now for each of these nodes, we're keeping track of their domain. And we're going to keep removing values from each of these nodes' domains. So we start off and assign blue to the first node, to this node here. What's going to happen the moment we assign blue to this node here if we do forward checking? Well, what does forward checking do? It removes values from domains of the other variables. So what's going to happen to which domains are going to be affected here? Anyone? The connected ones, okay, so this one and that one, and we're going to remove blue from that. So let's see that happening. Bam, blue is gone from this and that. We move forward with our next one. We assign red. Now red is gone from this guy. We move forward, blue, red, and so now from this one we remove blue and red. Notice that at this point, we already have a problem because these two are connected and the only thing that they can both be is green, and that's not going to work out. We should already know technically, but with forward checking we don't, because we don't look at, okay, I removed green from this, now let's propagate this forward and say, now this can't be green, and so there's nothing I can do with this one, so we're in trouble. That's not forward checking, right? Forward checking just looks one step ahead. So we don't know that yet with forward checking. We're going to get to our consistency, which actually does this kind of propagation. But with forward checking, all that we know is that, okay, now this has to be green. So we move on with our ordering. We take this one, we take this one, we take this one, and finally we get to here. And when we get to here, now this one, all of a sudden we know that we failed and we have to backtrack. All right, so let me let this play forward. Make it a little bit faster. A little bit faster. And then bam, eventually we actually have a solution. It takes less time than with just simple backtracking. So two things to note, right? Forward checking is actually, and I actually wrote them here so that I remember to tell you about them. So forward checking is different from backtracking. It actually detects failure earlier than backtracking. And forward checking still does not detect all failures, so we can still do better. Okay, and the way we can do better is we can actually start reasoning from constraint to constraint. Remember that situation where we knew that, okay, both of these things now have to be green, and I should know that I'm in trouble. We're going to use something called arc consistency to figure that out. So for arc consistency, we defined one new idea in this constraint satisfaction problem, the idea of an arc, the idea of essentially this directed edge. And we said, okay, pick any two variables that have a constraint, then pick one direction. It can be one direction or the other direction. We have two arcs. And then we said, this arc that goes from variable x to variable y is consistent. We're going to call it consistent if for every x in the tail, there's some y in the head, which could be assigned without violating a constraint. Okay, so let's see an example of this. Let's say I pick this arc. It goes from Northern Territory to Western Australia. And for it to be consistent, it must be the case that for every value in Northern Territory, there's something that I can assign in Western Australia that is consistent. Is this arc consistent? Who thinks this arc is consistent? Okay. Who thinks this arc is not consistent? All right, good. So what's the problem? What is the value that we would have to eliminate? Red. All right, so this arc isn't consistent because of this guy. This arc pretty much the same. And what we said we can do is we can actually eliminate, to make arcs consistent, we're going to eliminate these values that are causing us problems from the tail. And remember, constraint satisfaction police pulls you over, checks your trunk, you delete from the tail, okay? So that's the big thing. You're going to look at these arcs as having a head and a tail. We're going to eliminate values from the tail, from the trunk, that would put us in trouble in terms of finding consistent values at the head. Okay, so if you think of this definition of arc consistency, what arcs were we enforcing the consistency of when we were doing forward checking? Yeah.
Connected, just ones that were connected to the
Right, so we make an assignment, and then we look at, what were we doing in forward checking? We're looking at the variables that are neighboring that assignment and eliminating things from their domains that would be in conflict with the assignment we just made, right? So we were enforcing the consistency of all the arcs coming into the new variable that we just assigned. That's what forward checking is. But we don't have to stop there. We can enforce the consistency of more arcs than just the ones that happen to come to our new the variable that we just instantiated. So we can actually start talking about making all of the arcs in the CSP consistent. That means all of the edges in each direction, we can start making those edges consistent. So let's see what we would need to do for that. Let's look at this arc. Is this arc consistent? Who thinks yes? Who thinks no? Okay. So this arc, it turns out that if I assign red, I can assign blue. If I assign blue, I can assign red. And if I assign green, I can do whatever. So this arc is actually consistent. Let's remember this arc from V to NSW. That's consistent. We're going to come back to it later. Now, is this arc consistent? No? Why not? You were shaking your head no. Why do you think the arc is not consistent? Okay, so remember, for this arc to be consistent, it has to be the case that whatever I assign at the tail, I have some option at the head. The only thing I can assign at the tail is blue. If I assign blue at the tail, what value can I assign at the head that will be consistent? Red. Okay, so this arc is actually consistent. How about this one? No. Here we start to be in trouble because if I assign blue, then all of a sudden there's nothing I can do at the head, okay? So we have to remove blue to make this arc consistent. All right, so remember, we remove from the tail, we remove the values that get us in trouble. And now let's go back to this arc. This arc we just declared it consistent like 2 seconds ago. Is it still consistent? No, it's not consistent because if you actually assign here red, then we're in trouble. So to make this arc consistent, again, we have to delete red. Okay? So important, very, very, very important thing to note. Just because you make an arc consistent right now doesn't mean that afterwards, after you change some things, it's still going to remain consistent. And in particular, let's think about it a little bit more. If I have an arc with a tail and a head, is it okay if I remove things? So okay, if I have an arc from the tail to the head, and it's consistent. Let's say that some other arc makes me remove something from the tail of that arc. Is the arc going to remain consistent? Yes. And that's very important. If I just have something that goes from the tail to the head and I remove something from the tail, I'm still okay, because that arc being consistent said for every value in the tail, there's something in the head. Once I remove some value from the tail, it's still the case that for all the remaining values in the tail, there's still a value in the head, right? So deleting stuff from the tail is not really a problem. If anything, it makes consistency easier. It's one less value that you need to worry about finding something in the head. What about if I have an arc from the tail to the head, and because of some other thing, I remove something from its head? Is that arc still consistent? Not necessarily. Okay? So what we have to do when we go over these arcs and enforce arc consistency is we have to make sure that if you lose a value from an arc's head, then you check it again. And that's going to be important for the algorithm that actually enforces the entire CSP to be arc consistent. Okay. Now, arc consistency will detect failure earlier than forward checking. And the example is right there, still on the slide. So when I check this arc, if I have blue and blue, like we had green and green in our graph example, if I check this arc, I'll actually realize, oh, okay, I'm in trouble. This cannot both be blue, and I need to remove blue from the tail, and now I don't have any values left, so I can actually detect failure. Forward checking would not do that. It would have not necessarily. So let's do it. Let's say we're going to use arc consistency and see what happens. So we start off, we assign blue. Then we move on, we assign red. And now note that the moment let me go back. So when we assign red here, we're going to know that this can't be red. And then because of our consistency, when we try to make this node consistent, we're going to know that this can't be green. So here we assign red. Now this has to be green because this is blue and red. And because we looked at this arc as well, we removed green from this domain. So then we go forward. Now we assigned blue here, which means this can't be red, which means it has to be green, which means that now this one, thinking ahead one step, now this one can't be green, so it has to be red, okay? So our consistency just directly assigns green to this and doesn't have to get there and backtrack and get there and backtrack. It just directly knows what to do. And it nicely plows through this graph. And done. Much, much faster, right? It still needed to backtrack once, and we'll get to that in a second. But much, much faster compared to just doing forward checking. Okay, now, note that it's still backtracked. So we can run this in backtracking after each assignment, or we can run it at the beginning too. And what's the downside? Why would we do just forward checking and not arc consistency? Is there a downside to doing arc consistency? Yeah. Yeah, you do a lot more checking, right? So forward checking checks, let's say, the number of arcs that actually come into the new variable. Arc consistency has to check all of those plus a bunch more, and maybe some again. Yeah, question over there.
What do you mean by these like search process? Because aren't these things still exponential?
I see. Yes, and the worst case, of course, there's no free lunch, right? Constraint satisfaction problems are NP hard, and you just have to live with that. What I mean is that in practice, on average, you see that you do fewer checks, fewer backtracks, right? But that's at the expense of doing more computation at each assignment, at each step. So there's a trade-off there. And for some problems, that trade-off is going to make sense. For others, not so much. Okay. Very good question. Good. So here's the pseudocode. As usual, we're not going to go in great detail on this, but you have it on the slide to refer back to. A few things that I want to point out about this is, so this is the pseudocode for actually, it's called AC3 algorithm, and it's kind of one of the leading algorithms in enforcing arc consistency. So what happens is you start off with a Q here, and the Q is initialized with all the arcs in your constraint graph, in all of the directions. So now what you're going to do is, for each arc, you're going to make it consistent by removing inconsistent values from its tail. So the arc goes from xi, this variable here is called xi, to xj. So xi is the tail, and we're going to remove values from xi to make it consistent. We're going to remove values from the tail. And now what do we have to do if we removed values from xi? What arcs are going to be affected by that because we remove values from xi? Arcs that we might have already checked and declared consistent, but now we might be in trouble. Which arcs are affected if we removed, yeah?
All arcs coming from xi? Or
From or to? Yeah. So what did we say? We said if I have an arc that was consistent and I remove something from its head, then I might be in trouble because now I have fewer options in the head, right? And if I have fewer options in the head, then it might no longer be the case that for every value in the tail I'll find something in the head because I just removed an option or maybe even more from the head, right? So if I remove values from xi, I need to make sure that I add all the things that have xi as a head back in the queue because those might not be consistent any longer. And that's essentially the algorithm. You just go through this until you have nothing in your queue anymore. What is the runtime? Well, let's think through this a little bit. How many arcs do we have sort of in the worst case if we have n variables? Okay, this is a much simpler question than it seems. I have a graph with n nodes. How many possible arcs are there between two nodes of the graph? N squared, very good. So I have n squared possible arcs. Now to check an arc and make it consistent, what's the worst case runtime of that? If I give you an arc and I say, check that it's consistent or make it consistent. If the number of values that each variable can take is d, what's going to be the worst case runtime of making an arc consistent as a function of d? No one? Well, so let's think through what happens. We have one variable and it has d possibilities. That's the tail. We have the head. It has d possibilities. We have to make sure for everything in the tail, so for all of d possibilities, we have to make sure that there's something in the head. And that requires d checks in the worst case, right? So in the worst case, we go through d times d equals d squared operations to check one arc. And we have n squared arcs. But is it enough to check each arc once? No. We just said that we have to maybe add things back. In the worst case, worst case, how many times are we going to check an arc?
Every time.
When do I put an arc back in the queue? Well, we have the pseudocode right there. At what point do I put an arc back in the queue? Come on, help me out here. Yes.
Well, so when you remove something from the head of that arc, but I also have a question. If a queue is first in, first out, doesn't that arc get added to the end of it? And what do you graduate way later on after you're done with that?
It doesn't matter where you add it, right? It just matters that every time you touch something, you put it back so that you look at it later. And you're going to keep doing this until there's nothing left in the queue. Yeah. So her answer was right. we put back an arc whenever we eliminate a value from the head of that arc. How many values could we possibly eliminate at most from the head of an arc? D, okay? So the runtime is we have n squared arcs. It takes d squared computation in the worst case. We have at worst n squared arcs. It takes at worst d squared computation to make it consistent. And then finally, we might have to do this in the worst case d times. So it's on the order in the worst case of n squared d cubed. It turns out you can make that a little bit faster. Okay, note one thing, which goes back to your question over there, which is that this runtime is very much polynomial, and yet detecting all possible future problems is NP hard. Solving a CSP is NP hard. And so why? Well, why? Because we actually might need to backtrack. This is not going to give us a solution. In fact, after enforcing our consistency, we might find ourselves in one of three cases. We might find ourselves having only one solution left, multiple solutions, or no solutions left without knowing it. Okay? So let's look at a couple examples here. Let's look at this top example. So with this top example, let's look if it's arc consistent. Here's one arc. Is this arc consistent? Yes. Is this arc consistent? Yes. Is this arc consistent? Why not? All right, yes it is. Because if I assign green, I can assign blue, and if I assign blue, I can assign green. So we're in good shape. Is this arc consistent? Same thing. Okay, and these ones as well. So this is consistent. How many solutions are left here? How many solutions do we still have in the CSP? 2, that's right. Because we have blue, red. Oh, sorry, we have red here, green here, blue here, or vice versa, red, blue, green. All right, so this is an example where we still have solutions left, and there's actually multiple of them still left. Now let's look at this guy over here. All right, is this arc consistent? Yes, it's much like this guy's over here. So this is arc consistent. Every one of them looks identical. So this whole CSP, entire CSP is arc consistent. How many solutions are left? 0. Okay, so it could be the case that there's a failure, but we don't know it. And we get there and we realize, oops, and we have to backtrack. So full arc consistency is not necessarily enough to guarantee that you've detected all failures that could occur. It does detect failure early than forward checking. Forward checking detects failure earlier than doing no filtering, but still that doesn't mean that you actually can detect all failures. Now there's a bigger gun. Now we're bringing in the big guns. So that little guy, robot over there, that was our consistency. Now we're bringing this guy. That guy is called K consistency. So with K consistency, that just generalizes the idea of arc consistency, right? So for arc consistency, you can think of it as 2 consistency, where you can say that, let's see, for each assignment here at the tail, I guarantee that there's a consistent assignment with that for the head. K consistency basically says if I have K nodes and I split them into K minus 1 here and a Kth one, then for every consistent assignment that I can do for the K minus 1 nodes, I guarantee that I'm going to be able to find a Kth assignment that is consistent with the K minus 1. So that's the idea of K consistency. For each K nodes, any consistent assignment to K minus 1 can be extended to the Kth node. And it's a generalization from 2 to K. Of course, the higher the K, the harder it is to compute, right? And yeah, you'll need for this course to know the case of K equals 2, which is our consistency. Now, the even bigger gun is something called strong K consistency. Strong K consistency basically means that you have not just K consistency, but also K minus 1, K minus 2 consistency, all the way until 1 consistency. And my claim is that if you have strong N consistency, then you can solve the problem. That's when you can solve the problem without backtracking. Why is that? A little bit tricky, but if you have, you can do an inductive algorithm here, inductive proof here. So let's say you have n consistency. What you can do is you can pick one variable, any variable, choose a value for that, assign it. And then you choose a new variable, any other variable. And then you say, well, because I have two consistency, right? Because if I have strong inconsistency, I also have two consistency by definition. If I have two consistency, then that means that for any assignment that I made to my first variable, there's a consistent assignment for my new variable. That's what two consistency means. It's our consistency. Okay, so by two consistency, we have a consistent choice for the second, consistent with the first. Now we choose a new one. By three consistency, whatever we chose for the first two, there's something that we can choose for the third one. And so on and so forth until we get to n. So strong inconsistency actually guarantees that we can solve the problem without backtracking. Strong inconsistency is very difficult to get. Yes?
How would you even get true consistency of like algorithms? Unless you go through true consistency, don't you need to check that like any two adjacent nodes are consistent before you look at the third one?
No, so if you have three consistency, that doesn't mean you have two consistency. It just says for any consistent assignment of the two variables, there is something. But there might be no consistent assignment. Let's get back to that maybe in a discussion session. I think that's an interesting question. Okay, so thing to point out here, lots of middle ground between 2 and n, and there's k equals 3. That example is called path consistency. And that is filtering. Okay, so filtering can really help because you check failures early. The next thing that we're going to touch upon is going to be ordering. But let's take a quick 2-minute break first. so far we've talked about eliminating things and making sure that we detect failures early. Now we've gone through this backtracking search, and we've picked some ordering of the variables. But we weren't really smart about which ordering we're picking, right? We weren't really smart about, okay, which variable should go first, and given that I've done this variable, which variable should go next? And it turns out that there are things you can do that can actually really, really help in the search on that front. So ordering is about choosing variables in the correct order and also choosing values for these variables in the correct order. And in particular, the main strategy that people use is something called minimum remaining values, also called most constrained variable first. So the idea with MRV is that we're going to choose, when we're in the search, we're going to look at the variable domains, everything that's left, and out of all the remaining variables, we're going to pick the next one to assign to be the one that has the least number of values in the domain. How do we know? Well, because we've done some sort of filtering or something that estimates how many values are still left in that variable's domain. So what does that mean? Well, in the beginning, everything still has the same domain, so we just pick one. We break ties in some way. So let's say we go to our favorite, Western Australia, assign it red. Now we have a choice, right? Now we have to talk about, well, which variable to assign. And here's the question. Let's compare this one and that one, right? How many values does this one still have left? 3. How many values does this one have left? 2. So we're going to go to this one and assign it not red, but green. And then we're going to go to that one in the south there, because now if I compare this one to these guys, this one, how many values does it still have left? 1. So I might as well assign it the value and then see what happens afterwards, right? I'll have to eventually assign it blue. So if I don't do it now, later I might have assigned something else that might have made blue not work anymore, or something like that, right? So the idea is, at every point we're going to look at how many values each variable still has, and we're going to, the case of one value remaining is an extreme case, but you might have a variable with 5 values versus one variable with 3 values. You're going to choose the one with 3 values, given a choice. Now, why do this? Why would we make our lives hard and sort of go down the scary path and pick the variable that has the least number of values left, the most constrained variable? Why would we go there first instead of going to somewhere where it's easy? Yeah? You want to fail early, and actually, this ordering is also called fail fast ordering, right? So the idea here is that eventually in our search, we will have to go and assign that variable something. And so the longer we procrastinate, the worse it might get for that variable, and the harder it might be to assign it something later on. Okay? We will have to get it at some point, so we might as well do it now. Lesson in life, procrastination, not the right thing to do in CSPs, not the right thing to do in life either. All right? So, very important, minimum remaining values, or most constrained variable first. Let's see a demo of this at work. It's kind of fantastic what happens. We're going to go back to forward checking, because this graph is simple enough that it works well with our consistency. So you can just do forward checking to really see the advantage of this ordering of variables. So here's what's happening. We assign our favorite variable, our favorite value, blue. And now this guy has 2 values, this guy has 2 values. So we break ties in some way. We go here, we assign it red. But now, because of forward checking, we know that this has to be green. So instead of like moving on here and doing stuff and then figuring out, oh, well, actually now this can't even be green anymore, so I have to backtrack, we're just going to go there. We're going to go there, we're going to assign it that, and be done with it. Now, here again, instead of moving on just because now we don't have anything that has to be something, we're instead going to go to the most constrained one. We're going to go to this one, which only has 2. Right? Why? Because it's already kind of in trouble. It's down to 2. We do something, it might be 1, and it's getting scary, right? So we go there, we handle that. That reduces the domain of this. We go here, we handle that, and I'm going to let this play. And what you see is that it doesn't go through this typical ordering. It just kind of chases these constraints around and kind of puts out all the fires so that they don't turn into huge fires, I guess, later. And it's done. Yay! All right. Ordering really, really matters. Very good. So this was how we order variables in our search. There's still one more choice to make, which is, okay, we have a variable, it's the most constrained one, say, and it still has a bunch of values. Which one do I pick first? Well, for values, we go with the least constraining value. Okay? So the idea here is that I'm going to look at the possible values. I'm going to look at the one that rules out the fewest values in the remaining variables, and that's the one I'm going to pick. How do I know how many values it rules out in the remaining variables? Well, I have to rerun filtering or do something like that. Like pretend that I assign this value and then see what consequences are. So it does require some computation. But here's an example. Let's say that I'm in this situation. I assign red here. I assign green here. And now, for some reason, maybe my variable ordering, because I'm not doing the most constrained variable first, says do this one. So now I have a choice. Should I assign blue, or should I assign red, or should I assign blue here? Who thinks red? Okay, who thinks blue? Who abstains? All right. So let's reason a little bit through this. If I go here and assign red, how is that going to affect what happens to this variable? What choice am I still going to have? Blue. If I assign blue here, what choice am I going to have for this variable? Nothing. That doesn't seem good, right? So I actually want to go and assign the thing that's going to give me the most options in the future. So I want to assign red. Now, so notice that we're doing least rather than most here, and that's because unlike with variables where we have to get to that variable eventually, so we might as well do it now, with values, we don't have to get to that value. We don't have for every variable to assign every value. In fact, we have to assign only one value. So we might as well take the most promising one that makes our life the easiest in the future going forward. So here we don't choose the scary path with the monsters, we choose the nice, simple path. And that's ordering. Now, combining these ideas, I don't know if you remember the n-queens problem from last time. I am told that before ordering, you could do n equals 25. After ordering, you can do n equals 1,000. So ordering, pretty powerful in practice. All right, and finally, we're getting to structure. And that goes back to this constraint graph that we had, where we can try to exploit that not everything is connected to everything, essentially. Okay, so let's remember the constraint graph. The constraint graph had nodes, and then we had edges between the nodes if those two variables had a constraint between them. And the extreme case of structure, the nicest case, is when we actually have these subproblems that are totally independent, like Tasmania here, right? So Tasmania doesn't have any constraints with anyone. It's its own connected component, and that's really cool because we can just assign it whatever we want, right? So we don't have to treat it in combination with the other ones. We can just solve it separately and then solve the other ones, the rest of the graph over here, separately from that. Good. So now, let's say that I have a graph with n variables, and I actually identify that it can be broken up into connected components, separate connected components, and each connected component has about c variables in it. Let's assume that. Note that the worst case, the number of possible assignments I have, right, so the worst case complexity, is actually kind of nice, because what do I have? Well, I have In each connected component, I have C variables, so that's d to the C possible assignments. And then how many connected components do I have? Well, I have n variables, and each connected component has C variables, so I have n over C connected components. Okay? So the running time is, the worst case scenario is, for each connected component, I have to do d to the C work, and there's n over C connected components. And that's really nice. If C is low, this is really, really nice because we go from d to the n to something that's linear in n and is actually exponential in only C, which is much lower. This matters a lot, and let's see an example. Let's say n equals 80, and we have connected components of size 2, so 2, 2, 2, 2, 2. No, sorry, we have connected components size 20, and the domain is equal to 2. So n equals 80, C equals 20, D equals 2. If I solve this variable, the CSP, right, without explaining the structure at all, I'm going to have d to the n, that's 2 to the 80 possible assignments, okay? So it's going to take me, if I go at 10 million nodes a second, 4 billion years to go through all of them and check them, and that's the worst case complexity. So 4 billion years is, well, a little bit younger than the age of our planet Earth. Probably don't want to wait that long for this thing to solve your CSP, okay? But if we actually take advantage of this kind of structure, we only have n over c, that's 4, times 2 to the 20. Now 20 you might think is still big, it's still a lot of variables. What's the big difference between 80 and 20? Well, when you deal with exponentials, there's a big difference between 80 and 20, and you can solve this thing in 0.4 seconds. Okay, so you go from the age of our planet to 0.4 seconds. It's really nice when you have these different subproblems, different connected components. Really good thing to reason about in advance and exploit. Now, everything's peachy with these connected components, but guess what? In the real world, usually don't have nice separate connected components. So that's kind of a bummer, but there's another thing we can do, which is what if, okay, maybe we don't have connected components, but maybe we don't have edges everywhere. Maybe we have a tree. Maybe our constraint graph looks like a tree. It will turn out that if our constraint graph looks like a tree, meaning it has no loops, then the CSP can actually be solved in order in d squared time compared to d to the n. So also linear in n. Let's see how that works. Here's an algorithm, and then we'll show that it's linear in n, and we'll also show why it works. So let's say we have a CSP, and it's like a tree. And the first thing we do is we pick kind of a root, and like an ankle, and we shake it so that it actually falls down nicely and it looks like a tree. And we arrange it in some linear order like that. Good. So now let's say that each of these variables have some domains. We put them over here, running with our map coloring example. This algorithm proceeds as follows. It has a backward pass, and the backward pass says going from away from the root towards the root, right? So go from, in this case, from F towards A. We're going to make these arcs consistent. So let's do that. Let's start at F. Here's the arc that goes into F. Remember, this is a tree, so there's only one arc that goes into F. Is this arc consistent? No. We actually have to get rid of blue here. Let's get rid of blue. Okay. Now let's look at E. This is the arc that goes into E. Is this arc consistent? Yes. Good. Now let's go to D. This arc goes into D, B to D. Is this arc consistent? Yes. Now what about C, B to C? Is this arc consistent? No, we have to remove green. Okay? And then finally, we have A to B. Is this arc consistent? No. What do we have to remove? Blue. All right. So remove blue. Now the second part of this algorithm, okay, remove from the tail. Okay, so the second part of this algorithm says, now do a forward pass, where you start at the root, you start at A, and then assign things. So let's say we start at A. The only thing we can do is assign red. Now we go A to B. Well, there's a consistent thing here because we just checked this arc and it was consistent, so we know there's going to be something consistent. We go A to B. Good. Now B to C. If this is blue, we can assign green here. We know this is consistent because we checked this arc. Now B to D. Let's make it interesting. So B is blue. We can do either red or green. Let's pick green. D to E. Well, it can't be green, but this arc was consistent, so we have something left here that's blue. And then finally D to F. Okay, we go to F, we assign blue, and we have a consistent assignment. Yeah?
Can we not pick like the value that gives you the minimum number, or like the maximum number of like possibilities?
No, so the trick here is that you don't have to. Because this is a tree, and we're going to prove this in a second, the forward pass is guaranteed to not backtrack. Okay? And that's because we went ahead and made all those arcs consistent. And now, because this is a nice tree, basically what happens is for every arc that we're going to look at, every variable is going to have one arc coming into it, right? And so once we pick the parent, we're guaranteed that according to that arc being consistent, we're going to have something for that variable. And now we go to the next variable. Again, we picked something from the tail of that arc. We're going to have something at the head. Now this is order ND squared, and that's because we have basically checked, we did a bunch of arc checks, so that's where the D squared comes from, but we only looked at n of them, because this is a tree, there's n nodes, every node has one arc coming into it, and then that's it. ND squared. The claim is that after backward pass, all root to leaf arcs are consistent. So that's the claim one. That it's somehow enough. Note that we made a bunch of arcs consistent, but we never added arcs back on. And the claim is that that's enough. That if we go from the leaf to the root and we make all arcs consistent, we never have to revisit arcs again. That is the claim. Now, why is that true? Well, it's true because essentially because this is a tree and we're exploiting this, every node will have one parent. So as you go through this tree from the leaf, once you've made, let's pick an arc. Let's say I look at this arc. If I make this arc consistent, I'm going to do it by removing from the tail. And all the next arcs that I'm going to be looking at never touch the head again. And remember what rule, right? We discovered together that if I remove something from the head of an arc, then I have to check it again. But if I remove something from the tail of an arc, then I'm fine. And because this is a tree, I'm only ever going to be removing things from the tail. I'm never going to go backwards and look at some other arc that goes from D to something. Okay, so I'm never going to remove values from D again once I've touched that. And so that's the trick here. It really exploits the fact that this is a tree and that every node only has one parent. And it means that I never, once I check an arc, I never, ever, ever touch its head again. I might only touch its tail, and that's fine. That only makes consistency easier, not harder. And now once we have that, the other claim is that if we have this, if all these arcs are consistent, then forward assignment will not backtrack. And that's really by the very definition of these arcs being consistent. For every arc that I pick, let's say again, I look at this one. For every arc that I pick, because it's consistent, I know that whatever I assign here, there's going to be something that I have here, right? So you can start at the root, you can assign something, there's going to be something for the next one, something for the next one, something for the next one, and so on, because these arcs are all consistent. So this is an induction on position. Now, we already answered this. Why doesn't this algorithm work when you have cycles? Because you might actually have two parents for one node, and checking arc consistency for one doesn't mean that you'll not revisit its head and have to remove things. Okay. So, good. So let's recap. With structure, if we have separate connected components, we're good. We can go from 4 billion years to 0.4 seconds. That's nice. But that doesn't often happen. If we have trees, we're good. We're linear time. That's great. Guess what? It doesn't often happen. Usually your constraint satisfaction problem is not going to be a tree. So, but there's things you can do. And in particular, the thing you can do is try to make it into a tree. And the way you do that is do something called conditioning. The idea with conditioning is that I'm going to search for something called a cut set. I'm going to search for a set of variables such that if I remove those variables from the graph, I get a tree. So in that case, if I remove SA, I have this nice tree structure here. And we're going to do something called conditioning where we're going to say, I'm going to instantiate those variables. In this case, I'm going to instantiate SA, look at all possible assignments to SA. And then for each of them, I'm going to prune the neighbor's domain. So I'm going to, like if I assign this red, I'm going to remove red from here, remove red from here, remove red from here, and so on. And then I'm going to go to this nice tree structure that has some restricted domains. And I'm going to solve my CSP there using the tree algorithm that we just saw. So cut set conditioning says instantiate in all ways the set of variables. This is going to be the cut set, such that the remaining constraint graph is a tree. And so that's nice, because if you think about it, the running time is, well, you're left with a tree, so that's d squared times the number of things that are in the tree. So if we have a cut set of size c, then we have n minus c variables left after we take the cut set out. Good. And then we have to look at all possible assignments of the cut set, and that's d to the c. So if you have a really, really small cut set, like c equals 2, 3, 4, 1, even better, then things are in good shape. Because again, you're linear in n and only exponential in c. You only have to look at all the possible assignments of your cut set. If c is small, everything's good. So the algorithm is really simple. You start off with your full graph, and you choose a cut set. Now, how do you do that? That's a little bit hard. But you choose a cut set, you instantiate the cut set with all possible assignments. In this case, if you have one variable, SA, you instantiate with blue, red, or green. If you have two variables, you would do all combinations and so on. And then for each of these instantiations, you compute the residual CSP, that's a tree, meaning you take that node out and you look at you restrict the domains of the other variables such that they're consistent with this cut set assignment, and then you solve your residual tree CSP for each of these. That's all. Now finding a cut set is difficult, but finding a small cut set is okay because you can exhaustively search over all possible cut sets. Okay, what is the smallest cut set here? What nodes, who knows what nodes you can eliminate to make it a tree? Show of hands? Yeah. A and B. So if you remove A and B here, ta-da, let's say you get rid of those, then you have this nice tree structure. So that's nice. So that's the idea of using a cut set. And if you have small cut sets, then you're pretty much linear as well. So that's another thing you can do when you don't have connected components that are separate, you don't even have a tree. This cut set idea is, well, make it into a tree. And that means you make it into many trees, one for each possible assignment of your cut set, but that's still okay. And that's often very good in practice. Good. And now we get to the fun stuff, which is local search. So this is a little bit of a reset. And this comes back to one solution that one of you gave in the very, very, very beginning of last lecture when we started talking about constraint satisfaction problems. So when we started talking about constraint satisfaction problems, we decided that they could be search problems. And the particular definition of the search problem, the particular formulation we've been using so far has been your state is a partial assignment of variables, and your successor function takes one variable that is not assigned and assigns it something. That's been our running search paradigm. Now we're going to switch a little bit to a different formulation where we're actually going to use full assignments. So we're going to assign everything. And it's not going to be a consistent assignment. It's probably going to be very much inconsistent. It's going to violate all sorts of constraints left and right. And then we're going to iteratively try to make that assignment better and better and better, and that it violates fewer and fewer and fewer constraints. And that's an instantiation of a general algorithm called local search that works with optimization in general. And we're instantiating this now here for a very particular type of problem where the cost function that we're optimizing is how many constraints were violated. Okay, so the idea here is if maybe, let's say we have these two variables in our CSP, we're going to assign both of them, and we might assign them both red if we start with a random initialization. But not to worry, we can actually do this search where we define neighbors or successors as being take one variable and change it to something else. So here's the algorithm. Well, we haven't solved the CSP yet. We randomly select, any conflicted variable. And then we look at its neighbors, so to say, meaning we look at all the values that we could change that variable to. And then out of all those values, we pick the one that will cause the least number of constraints, least number of conflicts with the rest of the assigned variables. So for those of you who know hill climbing, that's hill climbing where the cost function that we're optimizing is the total number of violated constraints. Essentially, what's going to happen is you can think of this is your current state and it has a bunch of problems. I pick one variable and then I can assign it to a bunch of values. So that's going to give me a bunch of other states that I could possibly go to, one state for each value of the variable that I picked, and I will choose the one to go to that gets me in the least trouble. That's the idea. It's like this little, this kind of hilly space, and you have your little robot that can look around and it can go somewhere that seems a little bit better than the current position that it's in. Where position here is defined by a full assignment, and the goodness of a position is defined by the number of constraints that that assignment brings. So here's an example with the n-queens problem. Right, so we start off with this thing on the left, some random assignment on the left, and we have a ton of constraints that are being violated because these queens attack each other left and right. Now we pick one random queen, and in this case, we pick this random queen. And then we search for where to move it. We can move it anywhere, and we search for where to move it such that we get the fewest number of constraint violations. So if we move it here, we end up with only 2 constraint violations. These queens are attacking each other, these queens are attacking each other, but no one else is attacking anyone else. And then from there, we pick another random queen that's still in constraint violation, that's still conflicted. Let's say we pick this one, and we search for where to move it such that we have the fewest number of constraint violations. We can move it here, and we're done. I'm going to try to run a little demo. Okay, so here's this thing at work. Let's say I pick this queen. I start off with this terrible, terrible, terrible initialization. And I can move it somewhere, and I can move it to any of these, and I choose the least conflicting one. So I move it here. Okay, so now this queen is good, but we also have a lot of other queens that are in conflict. I choose another random one. I can move it here, that's good. Choose another random one. Now I can move it either here or there, and it will have 1, so okay. I choose this one. I can, let's say, move it here. Okay, this is not conflicting. I choose this one. There's not much I can do to it. I choose this one. There's not much I can do to it. And then I keep on doing this until eventually I solve the problem. Okay? So, yay, it took a while. Good. And then here on our favorite graph, there's an option to do this as well. So here's what this graph looks like when you do this iterative improvement. You start off, you assign everything randomly, and a bunch of stuff is going to be in conflict. So then you proceed by, at each iteration, you choose one of these nodes, and you pick a value to assign it to, a new value to assign it to. That's going to cause the least number of conflicts. So let's say we pick this, then we pick that, So we keep on changing these variables, eliminate conflicts, until finally we solve it. That was pretty fast, huh? Let's play that again. Ta-da! Done. All right. So what I want you to get out of this is that local search is a really, really, really powerful idea. It won't always work, but it's definitely a very sensible thing to try and think about whether it makes sense for your problem. What's the performance of doing local search in this way? Well, it turns out that if you look at n queens, I am told that in almost constant time, it can, with very, very high probability, it can solve n queens for an arbitrary n. That's pretty nice compared to the 1,000 that we could get with our ordering heuristics, right? Now, it turns out that there's kind of this constraint satisfaction problems are characterized in a sense by this ratio of you can look at the number of constraints that you have over the number of variables. And in a sense, for the same number of variables, if you have almost no constraints, right, then this ratio is really high. This ratio is really low. You're around here. And those problems are easy because you don't have a lot of constraints. Pretty much everything you do will work. And local search has a good time with that. Now, on the other side of the spectrum, if you have a lot of constraints, it turns out those problems are also really easy. Because if you have a lot of constraints, there's not a lot of good options, so you can actually very easily reason through it. The big problem is that when you're kind of in the middle, and there seems to be this ratio over here where, in that case, you start being in trouble. And this kind of graph is generated over randomly generated constraint satisfaction problems. So if you look at the landscape of all possible kind of constraint satisfaction problems, it looks something like this, where you have these nice green pastures for the most part, and this like bad volcano out to get you in this one small part of the space. And so these are the hard problems. Now, unfortunately, when it comes to real world problems, they don't follow the same distribution as randomly generated problems. And so it tends to be the case that with real world problems, you will also be here. But, you know, it's still worthwhile to try out local search. It performs well in a lot of cases. Good, so to summarize CSPs, all right, we've seen that there's a particular kind of a search problem, where we talked about states as being partial assignments, and we talked about a goal test being defined by whether you satisfy the constraints or not. Don't pack your bags yet, because we still have to talk about a couple more local search ideas after we summarize CSPs, just a word. Okay, so we've seen that we have this basic solution that's backtracking search, and that worked out really well, but then we also talked about these ideas where we start exploiting things that are related to the fact that this is a CSP to actually do better. We talked about how you can filter and detect failures much early so that you don't have to backtrack as much. We talked about ordering your variables in a really smart way, and we saw that basically that ends up looking like you're chasing the constraints and putting out fires, and that really makes a lot of sense and makes things easier. And we talked about structure, where we said, well, if you have kinetic components, everything's good. If you have trees, everything's good. If you don't have trees, but you almost have trees, then things can be really good there too. And then finally, we talked about a different paradigm of approach, where you actually do local search and just kind of locally, blindly look around in your local neighborhood and go to something that seems immediately better. Then you do that again and again and again. So that's what CSPs are. Now, because we started talking about local search, we wanted to share with you just a couple ideas from local search, really in order to point out that this is not specific to having constraint satisfaction problems. So let's see what's useful to go through. A particular kind of local search is something called hill climbing. That's what we were doing with these CSPs. Hill climbing is really, really, really general and really, really, really simple idea that in practice tends to be really, really, really effective. So the idea with hill climbing is that you might have some optimization or fitness function, and you're trying to go, you start off somewhere like here, and you're trying to go here. That's the ideal thing. But in general, you're trying to find some sort of solution that has a pretty good cost or pretty good fitness, pretty good score. So hill climbing says, okay, you start off wherever randomly, and then you repeat the following. You look at your neighboring states, you look around, and figure out what's the best thing to do, and it's going to be here, and you just get your robot to move there. And if you don't have any neighbors that are better than current, you just quit. When are you gonna face a situation where you are not gonna have any neighbors that are better than your current state? Yeah. A local maximum, right? So local optima are a big pain. So you might end up here in this case. You look around, everything looks worse. And you wish somehow that your robot would know that there's this direction and it's really useful, but it doesn't have that information. All it knows is it looks at the neighboring states and sees, well, I must be doing pretty well relative to my neighbors, and so I'm good. Things that can happen in classes too. Okay, so is this complete? Is it optimal? We already sort of saw that, right? It's not going to be optimal because you might get stuck in some local optimum. You might get stuck on that little hill there. But what's good about it is that it's really simple, it's really easy to implement, and in a lot of problems it works really well. It doesn't have guarantees, but in practice it can be really, really effective. The challenge is, and I'm going to tell you this from personal experience, it's not always obvious what the neighbor should be, right? So you usually know what the state is and you usually know what the cost function is, but you still have to decide what this kind of successor function or neighbor definition is. In CSPs, we basically said, well, our state is this full assignment, and our neighbor is going to be, we're going to pick one variable, and we're going to look at neighbors being all other values for that variable. And those assignments were going to be our neighbors. But it's not obvious. It's not always obvious what's a good thing to do. And so there's a lot of kind of creativity, so to say, or intelligence that goes into designing this neighbor function. And this is the kind of the diagram of what could possibly go wrong. So you have some global maximum somewhere, and that's where you want to be, but it really depends on where you initialize. If you initialize here, you're going to go to the global maximum. If you initialize here, you're going to end up in a local maximum. Sometimes you end up in this flat maxima where everything around you looks the same, and you're not going to know whether you should be going to something that is a different state but has the same fitness function or not, right? And then finally you have these shoulders, and it's hard to tell whether you're on a shoulder or whether you're on a flat local maximum. But in a sense, the good news is that if it doesn't work, you can try again. You can initialize, if you happen to initialize here and you're not happy with this outcome, you can initialize here, you can initialize there, you can keep on initializing, and in the limit, you'll finally get to where you need to be. Of course, that's in the limit, right? And the more tries you make, the harder it's going to be, the more time it's going to take. People have tried to improve on this with something called simulated annealing. The idea with simulated annealing is really simple, okay, instead of looking at all your neighbors and going to the best one, you're going to look at your neighbors, you're going to pick a random one, you're going to go there according to this probability distribution. The probability is going to be you're going to go there if it's better. If it's worse, you're sometimes going to go there. And that sometimes is defined by this notion of a temperature. It's an analogy from physics. There's this temperature that's high in the beginning, and it allows you to make steps in sort of downhill, not just uphill. And in the end, the temperature is really low, everything starts to settle, and you can only go uphill, you can never go downhill. But that's the idea with simulated annealing. And the very last thing is genetic algorithms. Genetic algorithms are probably the most misunderstood. We have one more minute, I promise. Genetic algorithms are the most misunderstood kind of local search. They're similar to hill climbing, But what they do in that, they still have a fitness function or a cost function that you're trying to optimize. They still have a mutation operation, that's what it's called there. We called it neighbor so far. But they introduced this new idea of a crossover. And this idea is, okay, instead of having one state and looking at its neighbors and going to the best one, then looking at its neighbors, going to the best one, we're going to have a bunch of states that we keep track of, like a swarm of solutions. And we're going to kind of breed them with each other. So that's what the crossover does. It's going to look at these solutions. When you do the selection part, you're going to tend to keep the solutions that have higher fitness and get rid of the ones that have lower fitness. It's kind of this natural selection kind of metaphor. Okay, so this guy's really good, we're gonna keep it, it's gonna end up being here and here. This guy's really bad, so we just completely throw it out of our swarm, kick it out, and then we're gonna make the best people breed with each other, crossover, right? And so what that means is that we have to find some operation where we actually combine two solutions. If you give me two solutions, I have to somehow mix them. And the hope with genetic algorithms is that if you define this kind of crossover operation right, you can take two solutions that are pretty good and turn them into a solution that's very good, and maybe a solution that's bad, right? So that's the idea. And you repeat this. You have the swarm, you breed them so that they get a lot of diversity, then you mutate them a little bit, and then you do selection again. Then you breed them again, mutate them, then do selection again. It can work nicely on the N queens in that if you have two solutions, and you cut the board somewhere and you say, I'm going to come up with a crossover where you take the first part of the board from the first solution and the second part from the second solution, maybe you end up with something where all of a sudden no queens are in conflict. Some of you look puzzled. I kind of am too. Crossover operations, they're hard to define right? But genetic algorithms have been shown to be really, really powerful when you actually find the crossover operations that make sense. But don't use a genetic algorithm if the crossover operation is just disastrous, right? You're just going to break good solutions, and your fitness is just going to go down in your swarm over time. All right, see you next time.